So you hear a lot, I hear a lot in my role, that folks who work in a lot of the omics fields, and maybe a little bit more so the proteomics, I don't know them in metabolomics, but that there are a lot of folks in that field who kind of focus primarily on the MS and maybe don't think about the chromatography step as being that important. Do you see that a lot, and do you, I don't know, do you have sort of an argument about that and say, hey, you really need to pay attention to your chromatography?
I would say it's very humorous to me when I've worked with people who will write their proposals and they say, we're going to use MS-based something to do proteomics or metabolomics. And I said, is it MS-based or LCMS or GCMS-based? You know, and just trying to make the point that separations are pretty important for what you're doing. And they always, they recognize it, but I think they are focused on the mass spectrometry. And I think it's true, you know, it's been the advances in mass spectrometry that have really driven this. I mean, the electrospray, the MALDI, the stability of mass spectrometers and how easy they are to use, and then all the new ones that have come, all the different types that have come out. That field's moved so fast, and it's really made a lot of this possible. There's no doubt about it. But I think at the end of the day, better chromatography is also helping. And so, you know, you can look at John Yates, and when he did shotgun proteomics, he used, the thing that made it work well was to put a two-dimensional chromatographic separation in front of it. And he knows that, and that's a big part of his mud pit invention that he had. And so I think many of the people who are detecting many metabolites or proteins really understand the power of separations. Another great example is Richard Smith's lab. He's really sort of dived into this ultra-high pressure business and making very high resolution columns. So he's got the highest resolution mass spectrometers you can get, and he still looks for the power of chromatography to really help that. So I think there's a lot of focus on it. It's the most expensive part of the effort, and you know, hundreds of thousands of dollars for machines. It's what's really evolved so much, but the better chromatography is making all, you know, is coming along and helping all that too. So,
are there ways to convince the unconvinced about this?
Well, I think, you know, some of the papers that, you know, that I just mentioned, Yates' original paper, I mean, just sort of remind people, you know, would you be doing shotgun proteomics without this two-dimensional thing on the front? And some of the really impressive work that Smith has had. Now, I can tell you that, you know, we recently, when Jorgens and I submitted our proposal on developing an ultra-high pressure LC to go in front of a mass spec for metabolomics, there was clearly some resistance from some people about, well, improvements in mass spectrometry are what you really need, not necessarily better chromatography. So we were able to pull, you know, when we went back for our revision, we were able to pull back some examples from the literature. There's a great paper by Ian Wilson who showed going from HPLC to UPLC dramatically improved the number of metabolites that he could detect. So that's another great example. So to me, it's an easy argument to win if you need to make it. And so I think overall people will appreciate it over time, and I don't think there's certainly some neat things you can do with just quick and dirty, shooting things in the mass spectrometer without separation or very minimal type separation. But when you're trying to go for lots of compounds, or often when there's specific targets you really need to hit, I think the separation is really making a big difference.
So the last question I have for you is almost going the opposite direction. So particularly in the earlier part of the conversation, we were talking about sort of what you're finding in some of these metabolomic studies and these complex metabolic pathways that you're studying. And I'm thinking, wow, it sounds like in your role you need not just to be analytical chemist, but biologist too.
Yeah.
So how do you cope with all that, trying to deal with all the biology of it all?
Maybe very slowly, I guess, is the answer to that. So we do have collaborators on these projects that often have ideas about and help us interpreting the data. But fortunately, I've been working in the islet, the beta cell field for many years, so I kind of have a pretty good understanding of some of the metabolism that's going on there, but not as deep as the people who really have been trained in that area, I guess. But it takes a long time to write the paper. I mean, you know, I find that if we just do an analytical development, we can do the experiments, and it may take a long time to figure out how to make everything work, but when it comes to writing up, it's not hard at all. That paper that was in the Journal of Biological Chemistry on the beta cells took forever to write. And part of it was working with the collaborator and getting their input and so on, but just tracking down all the pathways, making sure we had all the references right and that we were saying the right things was really, really time consuming and challenging. And I think you know, some of the neurotransmitters is a little bit easier because there's a limited number of things that we're looking at there. So it was not, those are a little bit easier to do because people generally have a hypothesis what neurotransmitter is being involved, and our data either supports it or it doesn't, and that's fine. You know, that tends to be a little bit easier. But yeah, the many pathways thing in the beta cells, very hard.
Yeah. Well, it certainly is fascinating, isn't it?
Yeah, yeah, it is. I mean, and you know, I've been very excited about, like, just to give you one example. You know, we discovered that when glucose goes into a cell, it actually, and this glucotoxic environment I was mentioning, it forms a metabolite called gluconic acid. It's not a natural metabolite, but it forms with the hydrogen peroxide that's in the cell from, and so this is a completely unexpected molecule there. It's not on any metabolic chart or anything, at least in mammals, and yet it's being produced, and it certainly could have some potential role in the toxicity that you see with these cells. So stuff like that, really exciting to see, you know, and also to have a student who really tracked it down and figured out what it was. I mean, that's fun for me to see them go to the effort to figure that out. It's really,
Well, Bob, thanks so much for talking to us today.